Okay, let's see. Okay, this is the presentation of my talk.
Perfect. Yeah, welcome.
So you are seeing it. Okay. Okay. First of all, let me thank the organizers for giving me this opportunity. I'm very happy to give another talk in Nizhny Novgorod, even though this time is through internet. I've been participating in Congress there in 2019, and I'm very happy to come again to another seminar in this place. I enjoyed very much that visit, and so when I had the opportunity, when I saw the opportunity to participate, and I really wanted to do it. Okay, so my talk is about a Lefschetz formula on stratified spaces. Okay, the general idea is the setting is compact stratified spaces with isolated singularities. This is for simplicity, because of course it can be done in more general stratified spaces. But just for simplicity, for a short talk, I will assume the singularities are isolated. And the regular stratum is endowed with a metric which is called adapted to the stratification. I will explain how it is. And the main goal is to give an analytic proof of a version of the Lefschetz formula for the L2 cohomology, which agrees with the intersection cohomology of lower middle perversity. There is a concept of intersection cohomology on stratified spaces, and it has a parameter, which is the perversity, besides having a degree, and the middle perversity, precisely the lower middle perversity, is what agrees with the L2 cohomology. And the main tool I will use is what is called the Dunkel harmonic oscillator, and it's the formations of this version of the harmonic oscillator, which was born in relation with quantum mechanics. Okay, the contents are these. I will explain the definitions and main theorems. The definitions I use, especially ideal boundary conditions and stratified spaces and adapted metrics. The main results, which are previous, which are needed, and then the Lefschetz formula. See, okay, and then I will say something about the proof. Well, about preliminaries, let me explain what is a Hilbert complex. A Hilbert complex is given first by a graded Hilbert space that I denote in this way. And then on that, I have a differential complex, which is given by a closed, densely defined operator on that Hilbert space, linear operator, which has a dense domain, and it is a complex in the sense that the square of D is 0. This concept was introduced by Bruning and Lech already quite a few years ago. And then we have the cohomology of this Hilbert complex. And we also have Laplacian, which is given in this way, taking this standard form of the Laplacian, taking the adjoint. And this is a self-adjoint operator in this Hilbert space. And there is what is called the smooth core of the Laplacian, which is the intersection of the domains of all powers of this operator. And it turns out that it defines a smooth soft complex, and it has the same cohomology And indeed, this smooth core determines the whole Hilbert complex, and it has the same cohomology. Okay. Now, let me talk about the important example is what is called an ideal boundary condition. For this, we take a Riemannian manifold, which is possibly non-complete. The important case here is that when it is non-complete, then we take the RAM differential and codifferential defined on compactly supported forms, on the complex of compactly supported forms. Then an ideal boundary condition for D is an extension of this differential on compactly supported forms to a Hilbert complex on square integrable forms on this Hilbert space. This is a greatest Hilbert space. So this would be a Hilbert complex in this Hilbert space. And there always exist ideal boundary conditions. And in particular, there always exists a minimum and a maximum ideal boundary condition. The minimum is taking the closure as a graph. So you get a closed linear operator, which is a complex also. And the maximum you can get is taking the adjoint of the codifferential. So this gives the maximum, which is also the adjoint of the minimum ideal boundary condition. Sorry, the minimum ideal boundary condition of the codifferential is the adjoint of the minimum boundary condition of the codifferential. So there always exists a minimum and a maximum ideal boundary conditions, and all other ideal boundary conditions are in between. Then we get also a minimum and maximum Laplacian corresponding to these boundary conditions. And if M is oriented, then indeed there is not much difference between them because the Hodge star operator defines an isomorphism between them. This Laplacian, the minimum Laplacian and the maximum Laplacian correspond one another by the Hodge star operator. Okay, but we have then the minimum and maximum cohomology for every degree, which is the cohomology of this Hilbert complex. And if then we have the minimum and maximum Betti numbers corresponding to the dimensions of these cohomologies for each degree. And if these Betti numbers are finite, then we have a corresponding minimum and maximum Euler characteristic. And these invariants depend on the quasi-isometric type of the metric. These are quasi-isometric invariants. And as I said, in particular, the maximum cohomology agrees with the L2 cohomology, which is defined with L2 forms, the differential acting on L2 forms. Now, if the manifold is complete, then the minimum and maximum ideal boundary conditions of the RAM differential on compactly supported forms agree. And so all ideal boundary conditions agree. So this is not the important case for us. We will consider cases where the manifold is not complete. So it is important for us that the manifold is not complete. So these cases will come from stratified spaces, the regular strata of stratified spaces. So now let me explain what is a stratified space with isolated singularities for simplicity. So this is going to be a compact Hauser space. I'm denoting it by A, and it is the disjoint union of a smooth manifold of dimension n, which is also called the dimension of A, and a finite set of singular points. the M is called the regular stratum, and these finite points are the singular stratum. Then for each singular point in the complement of the regular strata, there exists a chart centered at that point P, which is of this form. It takes an open set, an open neighborhood of that point, which I denote by O, sorry, to an open neighborhood in the cone of some manifold. Here, L is a compact smooth n-1 manifold, depending on P. For each singular point, for each singularity, you may have a compact manifold defining the cone. And this is called the link of the cone. Recall that the cone is just a quotient of the product of L times the interval, the closed interval 0 infinity, where we collapse the base L times C. And P corresponds to the vertex of the cone by this chart of stratified space. The vertex is the set that is collapsed, right? And so the regular stratum intersection, the intersection of the regular stratum with the neighborhood of P agrees with the regular stratum of the cone intersection with the image of that neighborhood. The regular stratum is the cone minus the vertex, which can be described as the product of L times the positive real line. And we have a special function, which is the radial function, which is induced by the projection on the interval 0 infinity. So on the cone, we have the radial function. Okay, I think I have the drawing. Well, let's first explain when it's metric adapted. A Riemannian metric on the regular stratum is called adapted if there is a chart as above at any point, at any singular point P, so that, okay, we have the chart in this way as before, and so that the metric is quasi-isometric to a metric of this form on the cone, on the regular stratum of the cone. This is just a conic metric, depending on the radial function in this way. And this G tilde is just any metric, any Riemannian metric on the link of the cone. So this is just a drawing of, to have an idea of how is stratified the space with isolated singularities. And then the singular points, for instance, this one has a neighborhood which is like a cone. And so that the metric which is adapted in the regular stratum is the regular stratum is just everything except the vertices. Sorry. Then it should be okay. This neighborhood should be quasi-isometric to the cone, to an open set of the cone around the vertex, so that the metric, the metric is quasi-isometric to this, which is just the conic metric for some metric G tilde on the link, and rho is just the projection along the radial direction. Okay. For us, it's important to consider also the metric completion of the regular stratum. The metric completion is denoted in this way, which is also a stratified space with isolated singularities. You can see here how the metric completion becomes a little bit different. The metric completion may have more singular points. 1 point gives rise to 2 points. Now, intersection cohomology. Intersection cohomology has a parameter, an extra parameter, which is called the perversity. Indeed, it is a sequence of parameters. And it was introduced by Goretzky and McPherson in the 80s. And for any adapted metric, we have that, well, there is what is called a lower middle perversity. The components of the perversity, the parameters involved in the perversity, has a range of values, of integer values, okay. And then there is a middle one. And sometimes there is a lower middle one, upper middle one, depending on whether the middle one is an integer or half an integer. Then, we take the lower middle perversity, then we have this isomorphism, which is between the intersection cohomology and the L2 cohomology, or the cohomology of the maximal ideal boundary condition. Of course, then if the regular stratum is oriented, then we also have an isomorphism with the minimum cohomology. But here we change to the first it was the lower middle perversity, and here the upper middle perversity. We have to change to the upper middle perversity. Well, this isomorphism was proved by Chigger, Goretzky, and McPherson in the 82. Okay. For general stratified spaces, the way to generalize things is to take charts with values in the product of an Euclidean space and a cone, but the link of the cone is also a stratified space of lower complexity. So this is defined by induction. The minimal complexity is when the link of the cone is just a compact manifold. And then you go by induction and increase the complexity. For instance, this is just a more general stratified space where you can see more strata. This point, this line, this curve, this strata here, which is just this stratum, which is just a surface, and this is another stratum, which is another surface. So we had a more involved partition into strata, which are smooth manifolds of different dimensions. And we can consider more general adaptive metrics of this. For instance, we can, instead of taking power, the square of the radial function, we can multiply the exponent by some number. If u, I don't know by u, if u is between 0 and 1, then the metric is like this. If u is greater than 1, then you get something like this. Okay. And well, this way of considering more general metrics give rise to isomorphism with intersection cohomology of arbitrary perversities, varying u. So we get a correspondence between perversities and the u's you can put, the exponents you can put for the metrics, so that for those perversities P, you get this still this isomorphism in the case where the perversity is less or equal than the lower middle perversity, and also for perversities greater than the upper middle perversity. But now you have to put the minimum ideal boundary condition. So this would be more general, and this was proved by Nagase a little bit later. So examples, first of all, orbit spaces of compact Lie group actions are stratified spaces. Also, leaf closures, the space of leaf closures of Riemannian foliations. Also, subanalytic subsets of Rn, which is difficult to prove. It is a result of Hironaka a long time ago. Pseudo-manifolds is a particular type of stratified spaces where you don't have a strata of codimension 1 at each step of the induction. But we continue using only stratified spaces with isolated singular points. So let me see some preliminary results I have to use. First, about the spectrum of the minimum and maximum Laplacian. We have proved, by the way, I didn't mention that this is with a student of mine. This work is with a student of mine called Carlos Franco. Then, about the spectrum of the Laplacian, of the minimum and maximum Laplacian, we have shown that for any good general adapted metric, it has a discrete spectrum, like this, which is like the spectrum of a closed manifold. But the way it grows may change with respect to a closed manifold. But anyway, there is some positive number so that it grows at least like a power of k, where k, a power with that exponent of k, where k is the order of the eigenvalues. So originally, this was proved by Chigger for adapted metrics. Let's see. I went too far. I think I have to go quickly, no? Okay, it was here. And okay, it was proved by Chigger. This part was proved by Chigger for adapted metrics. Also, there are related results by other people, more recent, for more general situations. And we have generalized it to the general adapted metrics I have said. And we also proved this second part, which is new. And the important point for us is that it involves a version of Moore theory, even though it is not involved here in the statement. We have to use a version of Moore theory.
Sorry for interrupting. You have 1 minute.
Only 1 minute. Okay, so let's go to the important result I wanted to mention. I went too slow then. Okay, so now let's go to the trade formula. We consider a stratified map, which is a map which maps strata to strata. So we only have a regular stratum, which is mapped to the regular stratum, and it is smooth on that stratum. And it maps the singular point to the singular points. And we assume for simplicity that the singular points are fixed. And then we also, if there are other fixed points, we assume that they are simple, which means this condition that the identity minus the differential is in isomorphism. And well, I already said this. And okay, and we assume this local expression with respect to the charts I have mentioned. And so the point X is in the link, and it is mapped to another point in the link with a smooth map in this closed manifold, which is the link. And about the radial function, it is mapped to the radial function times another function, which is the smooth function on the link. Then more general assumptions can be considered, but in this case, it induces an homomorphism in the minimum and maximum cohomology, and then we have a minimum maximum Lefschetz number, which is just the alternate sum of the traces on the minimum and maximum cohomology of each degree. And okay, on the other hand, we have the here this should be deleted. The Lefschetz number of the map in the link, defined with the usual cohomology of the link. And then this is the theorem we have proved, and that this Lefschetz number is a sum of the contributions from the fixed points, the usual contributions when we are taking fixed points in the regular stratum. And here we take, when we compute the contributions from the singular points, it is a sum of their Lefschetz numbers on the links of the maps defined on the links. And
sorry for interrupting.
Well, I should finish. Okay. Okay. Sorry. Sorry for being too slow, or perhaps writing too much. Okay. So I should stop. So thank you very much for your attention.
Let us thank the speaker. Questions, please. Any comments, maybe? Okay, then I have a question.
Yes.
In your opinion, what is the future of this research? What is the main ivory tower, maybe? What the best things one can obtain following this direction?
Well, the method is an adaptation of the proof of Witten for closed manifolds. And the point, instead of Witten uses the harmonic oscillator, and we have to use this Dunkel version of the harmonic oscillator, where which is quite interesting. It is a perturbation of the derivative, where on even functions is the usual derivative, and on odd functions is the usual derivative plus some multiple of the operator of dividing by x by the variable. For odd functions can be divided by the variable x, but given rise to another smooth function. So that's the Dunkel operator in this case. So the method is interesting, but I think considering stratified spaces, which is just the more general version of singular spaces, I know where you can make a standard, well, a version of the standard calculus, differential calculus. Well, it's very interesting because it represents many real situations. Usually, in the real world, you have singularities. Yes, you can apply, for instance, this to algebraic varieties. And so I think it is interesting. Of course, there was also a Lefschetz version of the Lefschetz theorem, trace formula, for stratified spaces originally proved by Goreski and Macpherson, but it is quite different. This is in this analytic way, with this analytic proof, one gets a different statement.
Thank you. Maybe one more short question. No? Then let us thank the speaker again.
Okay, thank you very much.